On a single night this past February, a telescope perched on a mountaintop in Chile looked up at the sky and sent out 800,000 individual alerts, each one flagging something that had actually changed since the last time that same patch of sky was photographed. An asteroid shifting position, a star flaring in brightness, a distant galaxy's core suddenly flickering. And that was just one ordinary night, because this specific telescope is eventually expected to generate up to 7 million of these alerts every single night for the next 10 years straight. And that telescope is the Vera Rubin Observatory. And in this video, I want to walk you through exactly what it actually is, what it's already found in its first year of real operation, and why astronomers describe it as fundamentally different from every other telescope that's ever come before it. So let's start with understanding exactly what makes this specific observatory so genuinely unusual, because it's honestly not really built to do the same job as a telescope like Hubble or the James Webb Space Telescope at all. Those instruments are specifically designed to stare deeply and patiently at one small, specific patch of sky for a long time, capturing an extraordinarily detailed, static portrait of a single distant galaxy or nebula. And Vera Rubin was built to do something almost entirely different. Instead of staring deeply at one small area, it's designed to photograph the entire visible night sky over and over again, every few nights, for an entire uninterrupted decade, essentially creating what astronomers themselves have started calling a movie of the universe rather than a single static photograph. And I think understanding that fundamental difference in purpose is genuinely the key to understanding why everything else about this observatory has been built the way it has. And I want to walk through the actual hardware itself, because the engineering here is genuinely remarkable and worth appreciating in real detail. The observatory sits at the summit of Cerro Pachón, a mountain in northern Chile, rising roughly 8,800 feet above sea level, a location specifically chosen because its combination of extremely dry air and minimal light pollution makes it one of the best possible places on the entire planet for this kind of continuous, wide-field sky observation. And the telescope itself features an 8.4 meter primary mirror, and connected to it is genuinely the single largest digital camera ever built anywhere in the world. A camera roughly the size of a small car, capable of capturing images so detailed and so wide that a single photograph would require hundreds of ordinary high-definition television screens just to display it at its full actual resolution. And this entire project, jointly funded by the U.S. National Science Foundation and the Department of Energy, represents an investment of roughly $800 million and more than 2 decades of, because it's honestly a genuinely stunning starting point for this entire story. One specific image combined 678 separate individual exposures, captured over just about 7 hours of observing time, and stacking that many images together revealed extraordinarily faint, delicate details that simply wouldn't be visible in any single instruments. And in that very first batch of test observations, comprising just over 10 hours of actual observing time, the telescope had already captured images containing millions of individual galaxies and Milky Way stars, along with thousands of previously uncatalogued asteroids. And I want you to actually sit with that specific number for a second, because it genuinely puts the observatory's eventual scale into proper perspective. Those 10 million or so galaxies captured during that very first brief test run represent something like just 0.05% of the roughly 20 billion galaxies. The observatory is actually expected to catalog across its full, planned 10-year mission, meaning even that genuinely impressive initial preview represented only the tiniest possible fraction of what's actually coming over the years ahead. And after that initial 2025 preview, the observatory spent additional time on further testing, calibration, and preparation, with its actual primary scientific mission, called the Legacy Survey of Space and Time, officially beginning full operations around mid-2026. After what astronomers involved in the project have described as a somewhat longer checkout process than originally anticipated, which is honestly genuinely common and expected for a scientific instrument this complex and unprecedented. And I think it's worth appreciating that specific kind of patient, careful calibration process too, because rushing a scientific instrument this sophisticated into full operation without adequate testing would risk generating flawed or unreliable data across an entire decade-long mission, making that additional care genuinely worthwhile, even though it meant a somewhat longer wait before full scientific operations actually began. And now let's talk about what the observatory's core mission, the Legacy Survey of Space and Time, or LSST for short, actually involves, because understanding its specific design goals genuinely helps explain why astronomers are so genuinely excited about what it's already producing. The survey is specifically designed to photograph the entire visible southern sky, roughly every 3 to 4 nights, continuously for 10 full years. And each time it revisits a specific patch of sky, its software automatically compares the new image against all of its previous observations of that exact same location, specifically looking for anything that's changed, a point of light that wasn't there before, an object that's moved position, a star that's grown brighter or dimmer, and whenever the system detects one of these changes, it automatically generates what's called an alert, a real-time notification sent out to astronomers all over the world within minutes, flagging that specific change for immediate further investigation. And that alert system is genuinely the single most transformative part of this entire observatory's design, because it means Rubin isn't simply building up an enormous archive of static images for scientists to slowly comb through later. It's creating a genuinely continuous, real-time stream of everything happening across the visible sky, night after night. And I think that distinction is honestly the key to why astronomers describe this project as so fundamentally different from anything that's come before it. And I want to walk through the specific kinds of cosmic events this alert system is actually designed to catch, because the range is genuinely broad and fascinating. Asteroids and other small solar system objects whose positions shift slightly from night to night as they orbit the sun, supernovae, the explosive deaths of massive stars, which can briefly outshine their entire host galaxy before fading away, active galactic nuclei, meaning supermassive black holes sitting at the centers of distant galaxies, that occasionally flare brightly as they consume surrounding material, and variable stars, meaning stars whose brightness naturally rises and falls in predictable, or sometimes genuinely unpredictable patterns over time. And Sarah Benito, a member of the observatory's own governing board, described the core value of this approach in genuinely evocative terms, explaining that if something in the sky moves or changes at all, Rubin will detect it and distribute that information out to the entire world in real time, allowing scientists to actually observe these kinds of transient, fleeting cosmic events as they're actually happening, rather than only discovering evidence of them well after the fact. And I think that specific capability, catching a rare cosmic event genuinely in progress rather than piecing together what happened from leftover evidence afterward, is exactly what makes this observatory so scientifically valuable. And now I want to walk through what this observatory has already actually found, because even in this early, relatively brief stretch of real operation, the results have genuinely been remarkable on a single night. Back in February of 2026, during early alert testing, the observatory generated 800,000 individual alerts. And once the survey reaches its full, planned operational cadence, astronomers expect that nightly alert volume to climb as high as 7 million separate alerts every single night. An almost incomprehensible amount of real-time astronomical data flowing out continuously to the global scientific community. And the observatory has already been directly credited with discovering new objects, including a specific main belt asteroid designated 2025 MN45, first spotted by Rubin's own Simone survey telescope back in May of 2025. And I think it's worth understanding that this kind of asteroid discovery represents just one small, routine example of the kind of solar system cataloging work this observatory is going to be doing continuously and automatically, essentially building out the most complete inventory of small objects within our own solar system that's ever been assembled, identifying and tracking asteroids, including specifically ones that could potentially pose any future impact risk to Earth at a scale and pace no previous survey has ever come close to achieving. And separately, astronomers have also used Rubin's early observational data to look backward through its own archive and identify precovery images, meaning images the telescope had already captured before a specific object was formally recognized and identified, of 3I Atlas, a genuinely rare and scientifically fascinating interstellar comet, an object that actually originated from outside our own solar system entirely, passing through on a trajectory that will eventually carry it back out into interstellar space permanently, and finding that this comet had actually already been sitting unrecognized in Rubin's own image archive before anyone had specifically identified and flagged it, genuinely illustrates one of the observatory's most valuable characteristics, because it continuously photographs the entire sky rather than only specific pre-selected targets. It ends up capturing objects and events that nobody had even thought to look for yet, sitting quietly in its data, waiting to be discovered later once astronomers actually know what specific thing to search for. And I want to spend a real moment on the deeper, longer-term scientific goals driving this entire project, because the day-to-day discoveries, genuinely exciting as they are, ultimately serve a handful of even bigger, more fundamental scientific questions. And I think understanding those goals helps explain why the specific observatory was considered worth building in the first place. One of the central goals is investigating dark matter and dark energy, two of the most significant, genuinely unsolved mysteries in all of modern physics. Dark matter refers to the invisible, otherwise undetectable substance that appears to make up roughly 85% of all the matter in the entire universe, inferred purely through its gravitational effects on the galaxies and structures we actually can see. And dark energy refers to the mysterious force that appears to be causing the universe's overay. All expansion to accelerate over time, rather than gradually slowing down the way earlier models predicted it should, and by precisely mapping the positions, movements, and subtle gravitational distortions of tens of billions of galaxies across the entire observable sky over the observatory's full 10-year mission, scientists hope to build by far the most detailed, most statistically powerful picture ever assembled of exactly how both dark matter and dark energy have shaped the large-scale structure of the entire universe over cosmic time. And separately, the observatory is specifically designed to build a comprehensive, detailed map of our own Milky Way galaxy, tracking the movement, brightness, and composition of billions of individual stars within our own galactic home, helping astronomers piece together a considerably more detailed picture of exactly how our own galaxy actually formed and evolved over billions of years. And it's also specifically designed to catalog small bodies throughout our own solar system at an unprecedented scale, asteroids, comets, and other minor objects, both for pure scientific understanding and for practical planetary defense purposes too, helping identify any object that might someday pose a genuine impact risk to Earth with enough advance, warning to actually do something meaningful about it. And I think it's worth appreciating that this observatory's 4 central science goals, dark matter, dark energy, mapping the Milky Way, and cataloging our solar system, were specifically chosen because they each benefit enormously from exactly the kind of continuous, wide-field, repeated observation this particular telescope was purpose-built to deliver, rather than being goals better suited to a more traditional, narrowly targeted telescope instead. And I want to talk about the sheer scale of data this project is actually generating, because I think that's honestly one of the more remarkable, underappreciated aspects of this entire story. Officials involved with the project have stated that Rubin Observatory will ultimately capture more information about our universe than every single optical telescope throughout the entire history of astronomy combined. And processing that almost unimaginable volume of continuous data requires an entirely dedicated computing infrastructure built specifically to handle it, with a portion of that critical data processing work actually happening at SLST National Accelerator. Laboratory in the United States, where a dedicated remote operations and control room has been specifically built to help manage and support the observatory's survey operations from thousands of miles away. And I think that specific detail genuinely illustrates something important about how modern, large-scale astronomy actually works today. A single observatory's scientific output increasingly depends just as much on the sophistication of the computing and data processing infrastructure supporting it, as it does on the raw optical quality of the telescope and camera themselves. And I want to address directly the specific framing in this video's own title, because I think it's worth being precise here. Are scientists genuinely stunned by what this observatory has already produced? And I think the honest, accurate answer is a genuine, well-earned yes, though I'd frame that reaction specifically as informed professional excitement and awe, rather than shock, in the sense of something being completely unexpected or surprising. Astronomers have been planning, anticipating, and actively preparing for this observatory's specific capabilities for well over 2 decades. Meaning what's genuinely stunning them isn't that the telescope works at all, it's the sheer, almost overwhelming scale and richness of what its data is already revealing, even during these comparatively early stages of full operation, discovering new asteroids, essentially automatically as an ordinary routine byproduct of its regular nightly survey work, catching a rare interstellar comet and retroactive precovery images before anyone had even specifically gone looking for it, generating a volume of real-time astronomical alerts that genuinely dwarfs anything any previous survey has ever produced. That's the specific, genuine, scientifically grounded sense in which experienced astronomers are describing themselves as stunned, not because the underlying physics or technology defies expectations in some inexplicable way, but because actually seeing this level of data volume and discovery rate materialize in real practice, after more than 20 years of careful planning and anticipation, genuinely exceeds what even experienced professionals fully, viscerally expected until they actually started watching it happen. In real time, night after night. And I want to close by talking about what comes next, because this entire story is honestly still just getting started. The Legacy Survey of Space and Time is a full 10-year mission, meaning the observatory has really only completed a small initial fraction of its total planned observing time so far, and every additional year of continuous operation will keep building an increasingly deep, increasingly statistically powerful archive of the changing sky, meaning genuinely major scientific discoveries, potentially including entirely new categories of cosmic phenomena that nobody has specifically anticipated or named yet, are very likely still ahead, rather than already fully behind us at this comparatively early stage. And I think that's honestly one of the more exciting, genuinely open-ended aspects of this entire project, because unlike a mission specifically designed to answer one narrow, predefined question and then conclude, Rubin Observatory was specifically built as a broad, continuous discovery machine, and some of its most significant findings may well end up being genuinely surprising, unanticipated phenomena that current astronomers haven't even thought to specifically look for yet. Precisely the kind of open, exploratory science this observatory's fundamental design was specifically built to make possible. And I want to bring this all together now with an honest, complete summary, because I think that's genuinely the best way to close out a story about a project this significant. The Vera C. Rubin Observatory, an $800 million, more than 2-decade-long engineering effort sitting atop a mountain in Chile, equipped with the largest digital camera ever built, is now actively conducting a 10-year survey specifically designed to photograph the entire visible sky repeatedly, continuously, generating real-time alerts about anything that changes, from shifting asteroids to exploding stars to flickering distant black holes. It's already discovered new solar system objects, helped identify a rare interstellar comet in its own retroactive archive, and it's on track to eventually catalog roughly 20 billion galaxies, an amount of astronomical data that genuinely exceeds everything every previous optical telescope in history has combined to produce, and its core scientific goals, understanding dark matter and dark energy, mapping our own galaxy in unprecedented detail, and cataloging our solar system for both scientific and planetaries. Defense purposes represent some of the most fundamental, significant open questions remaining in all of modern astronomy, and the genuinely honest, complete, and accurate story. Here isn't that scientists are stunned by any single specific image or discovery in isolation. It's that they're witnessing the beginning of what's very likely going to be one of the most scientifically productive astronomical projects in the entire history of the field, unfolding gradually, night after night, over the course of an entire decade. And I think that's honestly a far more genuinely exciting, complete story than any single dramatic headline about one specific stunning image could ever fully capture on its own, if this helped you understand the real, complete science behind this genuinely remarkable observatory. Hit subscribe, because we're going to keep bringing you accurate, in-depth breakdowns of real space discoveries as this incredible 10-year survey continues to unfold. See you in the next one.